Hello, I'm Alex. Beneath every star, every atom, and even the emptiest space you can imagine, a hidden engine is running nonstop quantum energy, and the rules behind it don't just shape the universe, they quietly shape you too. Tonight, we uncover what reality has been hiding all along. If this journey sparks even a bit of curiosity, a gentle like and subscribe truly helps. Now let's begin. Right now, at this very moment, you're disappearing and being reborn 7 billion times every second. Let that settle for a moment. Not metaphorically, not poetically, literally. The atoms that make up your body, the ones you think of as solid and permanent, are engaged in a constant invisible exchange with the world around you. Every breath you take introduces new atoms into your lungs. Every breath you release carries away particles that were just moments ago part of you. Your skin sheds millions of cells each day, each one a tiny constellation of atoms drifting away into space, settling on furniture, dissolving into air, becoming part of the room you're in. Scientists have traced this process with remarkable precision. They've found that roughly 98% of the atoms in your body are replaced every single year. The calcium in your bones cycles out over months. The cells lining your stomach renew every few days. Even the proteins in your brain, the very structures that hold your memories, are constantly being dismantled and rebuilt, molecule by molecule, like a building being renovated one brick at a time while people still live inside. Think about that for a moment. The body you had last year, the physical substance of it, is almost entirely gone. The atoms that composed your hands, your heart, your eyes, they've been swapped out, traded away, replaced by new ones pulled from the food you've eaten, the water you've drunk, the air you've breathed. And yet here you are, still you, still reading these words, still carrying the same memories, the same sense of self, the same quiet awareness that you are somehow continuous, unbroken whole. But if nearly every atom has been replaced, then what exactly are you? This paradox has troubled philosophers for thousands of years. The ancient Greeks told a story about a ship belonging to the hero Theseus. Over many voyages, the ship's planks rotted and were replaced one by one until eventually not a single original piece of wood remained. The question they asked was simple and unsettling. Is it still the same ship? Now, imagine that puzzle at the quantum level. Your body is not a ship of wood, but a ship of atoms, electrons, quarks, vibrating fields of energy, and unlike wooden planks that get swapped out over years, your atoms are exchanging particles constantly, billions of times per second. Virtual photons leap between electrons. Neutrinos pass through you as though you were empty space. Quantum fields that make up your matter are in continuous interaction with the quantum fields around you, blurring the boundary between where you end and the world begins. At the quantum scale, the idea of a fixed solid self starts to dissolve. You're not a static object, but a dynamic process, a pattern of energy that holds its shape for a while, like a whirlpool in a river. The water molecules that make up the whirlpool are constantly flowing through, entering from upstream and exiting downstream. Yet the whirlpool itself persists. It has form. It has structure. You can point to it and say, there, that's the whirlpool, even though the water is never the same from one moment to the next. You are like that, a persistent pattern in the flow of atoms and energy. What you call yourself is not a collection of things, but a relationship, a coherence, a rhythm that continues, even as the notes keep changing. And this raises a deeper question. If the matter that composes you is temporary, if it's constantly being replaced and exchanged, then what is it about this pattern that makes it you and not someone or something else? What holds the continuity? The answer lies not in the atoms themselves, but in the information they carry, the way they're arranged, the structure and order that persists beneath the flux. Your identity, in other words, is not written into particles. It's written into patterns, and those patterns are held together not by solidity, but by forces, by fields, by the invisible architecture of quantum mechanics that keeps everything humming in place, even as it flows and shifts beneath the surface. It's a humbling thought. The substance of your body is not permanent. The atoms you're made of are borrowed temporary guests in the shape of you. In a very real sense, you're not the matter, but the music, not the instrument, but the song being played on it. Perhaps that's why we sometimes feel untethered, as though something essential about us is hard to pin down. We sense, maybe without words, that the self is not a solid thing, but a kind of dance, delicate and continuous, held together by forces we can't see but can't escape. There's a certain beauty in that fragility. It means you are not separate from the world around you. The atoms that were once part of a distant star, that drifted through space for billions of years, that fell to earth as dust and rain, are now for a little while part of you. They form your bones, your breath, your thoughts, and when they leave, they'll go on to become something else, a leaf, a cloud, a wave breaking on some far shore. Nothing is ever truly lost. It only changes form. So, when was the last time you felt like yourself? Not the self made of flesh and bone, which is always shifting, but the deeper self, the one that persists beneath all the change. Maybe it's not a when, but a how. Maybe being yourself isn't about holding on to anything at all, but about letting the pattern flow, trusting that the music will keep playing, even as the notes move on. The matter you're made of is not what you think it is, solid and permanent and yours. It's fleeting, shared alive, with exchange. And that makes you not less real, but more connected part of a larger conversation between energy, form a quiet participant in the endless transformation of the universe. But if the atoms themselves are so temporary, so constantly replaced, then what are they really made of? To understand that, we need to look even closer, beneath the particles, beneath the substance, to the strange and shimmering foundation, where everything, even solid matter, begins to reveal its true nature. Here's a question you probably haven't asked yourself today. Why does this table feel solid? It seems like a ridiculous thing to wonder about. Of course, the table is solid. You can see it. You can touch it. If you knocked on it right now, you'd hear the dull, reassuring thunk of something undeniably there, something real and dependable. The table holds your cup, your book, your hands. It does not waver. It does not shimmer. It simply exists as matter, should firm and unambiguous. But what if almost everything you've ever felt, every surface you've ever touched, every object you've ever held, has been lying to you? The truth is this: the table is not solid, not even close. In fact, if you could zoom in far enough, past the wood grain, past the molecules, past the atoms themselves, you'd discover something astonishing. The table, like your body, like every object in the universe, is almost entirely empty space. Consider the atom. It's often drawn as a tiny solar system with electrons orbiting a dense nucleus like planets around a sun. That image, though helpful, doesn't capture the sheer scale of emptiness involved. If you could magnify an atom to the size of a football stadium, the nucleus, where nearly all the mass resides, would be no larger than a grain of rice sitting at the center of the field. The electrons, those infinitesimally small points of charge, would be buzzing somewhere out near the stands, flickers of presence in a vast and empty arena. Everything in between the space that makes up 99.999% of the atom is nothing, or at least it appears to be nothing in the classical sense. No particles, no matter, just the hum of quantum fields and the ghostly flicker of probabilities. Now think about the table again. It's made of atoms, billions upon billions of them, all packed together, each one a tiny hollow shell of mostly emptiness. If you removed all that empty space, if you could compress the table down so that only the nuclei remained pressed tightly against one another, with no gaps in between, the entire table, sturdy and broad as it is, would shrink to a speck smaller than a grain of sand. You could hold the mass of an entire table compressed on the tip of your finger, and it would weigh as much as a mountain. The same is true of you. If all the empty space in your body were removed, if every atom were squeezed down to just its nucleus, you would collapse into a particle so small it would be invisible to the naked eye. All of you, every memory, every thought, every experience you've ever had, condensed into a dot no larger than a speck of dust. And yet you'd still weigh the same. All your mass would remain packed into that impossibly tiny point. This is not science fiction. This is the architecture of reality. So why then does the table feel solid? If it's mostly empty, why doesn't your hand pass straight through it, like a ghost through a wall? The answer lies not in matter, but in force. What you experience as solidity is not the presence of stuff, but the presence of resistance. When you press your hand against the table, you're not actually touching it in the way you think. The atoms in your skin and the atoms in the table never make contact. Instead, the electrons in your hand and the electrons in the table repel each other through electromagnetic force, an invisible field of push and pull that keeps them apart. It's like trying to press two magnets together with the same poles facing each other. They resist. They push back. That resistance, that electromagnetic repulsion, is what you interpret as touch. It's what makes the table feel solid. But in truth, your hand and the table are separated by a thin veil of empty space, held apart by forces too small to see but too strong to overcome. You are not touching anything right now. Not really. You are hovering, always hovering, a fraction of a nanometer above every surface, held aloft by the invisible force fields of electrons pushing against one another. The sensation of touch is a trick, a convincing illusion created by your nervous system, translating electromagnetic repulsion into the feeling of contact. And here's where it gets stranger still. Those electrons, those tiny points of charge that create the illusion of solidity, are not really points at all. They are not little balls bouncing around inside atoms. They are something far more elusive. According to quantum mechanics, Electrons are excitations in a quantum field, ripples in an invisible ocean of energy that fills all of space. They exist not as objects, but as patterns, as waves of probability that only collapse into a definite position when observed or measured. In other words, the table is not made of things, it's made of interactions. It's made of fields overlapping, vibrating, pushing, and pulling in intricate harmony. The atoms are not solid blocks stacked like bricks. They are standing waves, resonances, fleeting knots of energy that hold their shape just long enough to seem permanent. This idea that everything is really a field, a vibration in an unseen medium, is at the heart of quantum field theory. It suggests that the entire universe is like an ocean, not of water, but of invisible fields, each one humming with energy, each one capable of producing ripples that we perceive as particles. The electron field ripples, and an electron appears. The photon field ripples, and light is born. The quark fields ripple, and the building blocks of protons and neutrons come into being. You, the table, the air, the light streaming through the window, all of it is made from these ripples, these vibrations in the quantum fabric of space. Nothing is truly separate. Nothing is truly solid. It's all one continuous medium, endlessly shifting, endlessly interacting, endlessly creating the illusion of form. There's something almost playful about it. Don't you think the universe's greatest magic trick? It convinces you that the world is made of things hard and separate and real, when in truth it's all just waves in an ocean. You can't see fields pushing against fields, energy pretending to be matter. And here's the part that might make you smile, or perhaps shiver just a little. You're not really touching the screen. You're not really sitting on that chair. You're not even really inside your body in the way you think you are. You're a cloud of probabilities, a swirl of electromagnetic repulsion, a symphony of quantum fields vibrating in the shape of a person. Your atoms are mostly empty. Your electrons are more like clouds than particles. And the sensation of being solid, of being here, is just your brain's way of making sense of forces it can't directly perceive. You've never truly touched anyone, not your loved ones, not your friends, not even yourself. Every embrace, every handshake, every gentle touch has been an exchange of forces across a gap too small to see a conversation between fields, a dance of particles that never quite meet. And yet somehow it still feels real. It still matters. The illusion is so convincing, so beautifully crafted, that it becomes in a way more real than the truth beneath it. The table holds your cup. Your hand feels warm against another's. The world, for all its emptiness, is full of presence. Perhaps that's the deepest magic of all, that something made mostly of nothing can still create everything we know. That emptiness, arranged just right, can become a universe. So if the solid world is mostly empty and touch is an illusion, then what fills the space in between? What hums in the quiet void where particles don't exist? The answer is stranger than emptiness. It's an ocean of invisible energy, restless and alive, waiting to reveal the next secret of the quantum world. If empty space were truly empty, the universe would be a very different place. In fact, it might not exist at all. We tend to think of a vacuum as the ultimate absence of void, where nothing happens, nothing moves, nothing is. It's the silence between sounds, the darkness between stars, the gap where matter has been removed and only nothingness remains. But quantum mechanics tells a different story. It says that even when you strip away every particle, every atom, every photon of light, what remains is not silence, but a low constant hum of activity. The vacuum, it turns out, is busier than Times Square at rush hour. This restless energy is called zero-point energy, and it's one of the strangest predictions of quantum theory. Remember Heisenberg's uncertainty principle. It says that certain pairs of properties like position and momentum can never be known with perfect precision at the same time. But there's another pairing that matters here: energy and time. The uncertainty principle tells us that over very short time scales, energy can fluctuate wildly, borrowing and repaying itself so quickly that the universe's accounting books never notice the discrepancy. What this means in practice is that the quantum vacuum is never still. Even at absolute zero, the coldest temperature theoretically possible, when all heat has been drained away and no particles remain, the fields that make up space itself continue to jitter and tremble. They can't help it. The uncertainty principle won't let them rest. These fluctuations give rise to something extraordinary: virtual particles. They're called virtual not because they're imaginary, but because they exist only for the briefest whisper of time. A particle and its antiparticle, say an electron and a positron, can suddenly appear out of the vacuum, flickering into existence, like sparks from a fire. For a fraction of a second, they're real, borrowing energy from the void. But almost instantly, they collide and annihilate, returning the borrowed energy and vanishing as quickly as they came. This happens everywhere all the time: in the space between your fingers, in the air around you, in the vast emptiness between galaxies. The vacuum seethes with these ghostly pairs, appearing and disappearing in a ceaseless dance that never quite tips into permanence. You might think this is just theoretical speculation, a quirk of mathematics, with no real consequence. But the universe has a way of making the invisible tangible. In 1948, a Dutch physicist named Hendrik Casimir proposed a test. He imagined placing two perfectly smooth, uncharged metal plates very close together in a vacuum, just a few billionths of a meter apart. According to classical physics, nothing should happen. The plates are neutral. The space is empty. There's no force to push or pull them. But Casimir's calculations, based on quantum field theory, predicted something astonishing. The virtual particles in the vacuum have wavelengths, and only certain wavelengths can fit in the narrow gap between the plates. Outside the plates, where space is unlimited, all wavelengths are possible. This creates a difference in energy density, a subtle imbalance, and that imbalance exerts a force. The plates, ever so gently, are pushed together by the pressure of empty space itself. Decades later, experimenters confirmed it. The Casimir effect is real. You can measure it. You can feel the vacuum pushing back. Now let's do a thought experiment, one that reveals just how much energy this invisible ocean contains. Imagine an empty coffee cup sitting on your table. Not a cup with air in it, but a true vacuum, every last particle removed, leaving only the humming quantum fields. If you could somehow extract all the zero-point energy from that small volume, just the space inside an ordinary coffee cup, how much energy would you get? The answer, according to some calculations, is staggering. Enough energy to power a city for weeks. Some estimates go even further, suggesting that the energy density of the vacuum is so immense that a single cubic centimeter contains more potential energy than all the matter in the observable universe. If that's true, then why aren't we tapping into it? Why isn't there a zero-point energy generator on every street corner, solving the world's energy crisis in one elegant stroke? The answer lies in one of the most fundamental rules of physics, the conservation of energy. Energy cannot be created or destroyed. It can only change form. And here's the catch. Zero-point energy is the lowest possible energy state. It's the ground floor of reality. You can only extract useful work by moving from a higher energy state to a lower one, like water flowing downhill through a turbine. But if you're already at the bottom, there's nowhere lower to go. Think of it like this. Imagine walking up to an ATM, inserting a card for an account that doesn't exist, and trying to withdraw money. The machine might display numbers, might hum and whir, but no cash will come out. The energy is there, in a sense, encoded in the vacuum's constant fluctuations. But it's not accessible. You can't dig beneath the basement. You can't extract work from a system that's already in its lowest state. This hasn't stopped people from trying, of course. The dream of limitless free energy is too seductive to resist. But every serious attempt has run into the same unyielding wall. The laws of thermodynamics. The vacuum's energy is real, but it's balanced, locked in place by the same quantum rules that create it. To harvest it would require breaking the universe's most reliable principles, and the universe, for all its strangeness, plays fair. And yet, even though we can't tap into it, the zero-point energy is not inert. It has consequences. It stabilizes atoms, keeping electrons from spiraling into the nucleus. It contributes to the Casimir effect, pushing metal plates together. Some cosmologists even suggest that it might be related to dark energy, the mysterious force causing the universe to expand faster and faster. The vacuum's restless hum may be shaping the fate of the cosmos itself. So, the next time you look at the space between your fingertip and the screen you're reading, remember this: that gap is not empty. It's teeming with invisible motion, a frothing sea of particles appearing and vanishing fields, fluctuating in patterns too fast and too small for your senses to detect. The void is alive. Emptiness, it turns out, is one of the fullest things in the universe. The space between your fingertip and this screen right now is seething with energy, a silent storm of creation and annihilation that never stops, never rests, and has been humming since the beginning of time. But if the vacuum hums with this hidden energy, where does it come from in the first place? To answer that, we need to look at the one place in the universe where energy reveals its true power, where the impossible becomes routine, and where a ball of fire has been burning steadily for more than 4.5 billion years. Here's a question that should bother you more than it does. How can something burn for 4.6 billion years without running out of fuel? Think about it. A campfire burns through wood in hours. A candle melts away in an evening. Even the largest forest fire, given enough time, consumes everything in its path and goes out. Yet the sun, that vast sphere of roiling plasma 93 million miles away, has been shining with nearly constant brightness since long before the Earth had oceans, before life crawled out of those oceans, before anything on this planet even knew what light was. It has outlasted mountains, it has outlasted species, and it shows no sign of stopping. So, what kind of fire can burn for billions of years? The answer is, it's not fire at all. The sun is not burning in the way we usually think of burning. It's not consuming oxygen, not turning matter into ash and smoke. Instead, it's doing something far more profound. It's converting matter directly into energy, transforming the very substance of itself into light and heat through a process that happens only because of quantum mechanics. At the sun's core, where temperatures reach 15 million degrees Celsius and pressures are unimaginable, hydrogen atoms are being fused together to form helium. This is nuclear fusion, the same process that powers hydrogen bombs, but happening in a slow, controlled, majestic way that has sustained our star for half the age of the universe. But here's the problem. For fusion to work, two hydrogen nuclei protons need to get close enough to stick together. And protons don't want to do that. Each one carries a positive electric charge, and like charges repel. It's the same force that keeps your hand from passing through a table, but amplified 1,000,000 times. The closer two protons get, the harder they push each other away, creating a barrier of electromagnetic repulsion so strong that, classically speaking, they should never be able to overcome it. Even at 15 million degrees, with particles moving at extraordinary speeds, the protons simply don't have enough energy to smash through that barrier. If the sun relied on classical physics, fusion would be impossible. The core would be a hot, dense ball of hydrogen glowing faintly from thermal radiation, slowly cooling over eons until it went dark. There would be no sunlight, no warmth, no life. But the sun doesn't play by classical rules. It plays by quantum rules. And in the quantum world, there's a loophole, a strange and a beautiful trick called quantum tunneling. Remember that particles are not solid little balls, but waves of probability. When a proton approaches the electromagnetic barrier, its wave function doesn't stop cleanly at the edge. Instead, it extends beyond the barrier, fading gradually, like an echo trailing off into silence. Most of the wave is reflected back, yes, but a tiny portion of it leaks through to the other side. That faint tail of probability means there's a chance, however small, that the proton will simply appear on the far side of the barrier without ever having climbed over it. It's as if the particle took a shortcut through a wall tunneling from one side to the other, through a path that classical physics says doesn't exist. The odds of this happening for any single proton are absurdly low, roughly 1 in a trillion. If you watched a single proton trying to fuse, you'd wait longer than the age of the universe before seeing it succeed. But the sun's core contains an almost unimaginable number of protons packed together under crushing pressure, colliding trillions upon trillions of times every second. In that vast lottery, even billion-to-1 odds become certainties. Enough protons tunnel through enough fusion happens, and the sun shines. When two protons successfully fuse, something extraordinary happens. A tiny amount of their mass disappears. It doesn't go anywhere else. It simply ceases to exist as matter and reappears as energy following Einstein's famous equation E equals mc squared. The c in that equation is the speed of light, a number so enormous that even a minuscule amount of mass translates into staggering energy. Every second, the sun converts about 4 million tons of matter into pure energy. 4 million tons, vanishing, transformed into the light that warms your face, the glow that makes plants grow, the radiance that has shaped every ecosystem on Earth. That energy doesn't appear instantly, though. A photon born in the sun's core begins a long, chaotic journey outward, bouncing and scattering off particles in the dense plasma, taking a random, drunken path toward the surface. On average, it takes about 170,000 years for that photon to escape the sun's interior and finally stream into space. So, when you step outside and feel the sunlight on your skin, you're feeling the result of a quantum event that happened deep in the sun's heart sometime during the last ice age, when woolly mammoths still walked the earth, and early humans were just beginning to paint on cave walls. The warmth on your face is a gift from a quantum tunnel that opened in an era long before recorded history. I know this story is starting to feel dense, layered with numbers and concepts that pile up like falling snow. But here's the thing. The secret at the heart of it all is simple. The sun burns, not because it's hot, but because the universe allows the impossible to happen just often enough. Quantum mechanics doesn't guarantee that tunneling will occur. It only says there's a chance. And given enough chances, given enough time, the improbable becomes inevitable. This is the deeper lesson. The universe is not rigid. It's not a machine running on fixed gears and predetermined paths. It's probabilistic, flexible, alive, with potential. Barriers are not absolute. Walls can be crossed. And the most fundamental processes, the ones that make life possible, depend on those fleeting, fragile moments when reality bends just enough to let something new emerge. Without quantum tunneling, stars would never ignite. Without stars, there would be no heavy elements, no planets, no chemistry, no biology. The fact that you exist, that you're reading these words, that you can think and feel and wonder, all of it traces back to protons tunneling through barriers in the hearts of ancient stars, releasing the energy that forged the atoms in your body. The sunlight warming your skin right now is a gift from a quantum event that unfolded deep in the sun's core during prehistoric times, a whisper of probability that became the light of day. And if quantum tunneling powers the sun, what else might it be doing in the hidden corners of reality? To find out, we need to step back and ask a more fundamental question. Why does anything ever change at all? The answer lies in one of the strangest principles ever discovered, a rule that says perfection is impossible, and that uncertainty is the very heartbeat of existence. If you could know everything about a single particle, every detail of its position and motion with perfect precision, you could, in theory, predict its entire future. You'd know where it would go, what it would do, how it would interact with every other particle it met. The universe would become, in essence, a vast clockwork mechanism, deterministic and predictable, ticking forward along rails laid down at the moment of the Big Bang. But the universe doesn't work that way. And we know this because of a principle discovered in 1927 by a young German physicist named Werner Heisenberg, a principle so fundamental and so strange that it rewrote the rules of what can be known. Heisenberg's uncertainty principle says that there are pairs of properties, like position and momentum, that cannot both be measured with perfect accuracy at the same time. The more precisely you know where a particle is, the less you can know about how fast it's moving or in what direction. And conversely, if you pin down its speed and trajectory with great exactness, its position becomes a blur smeared across space, like a watercolor left out in the rain. This isn't a technical limitation. It's not because our instruments aren't good enough, or because we haven't figured out the right technique. It's a fundamental law of nature, woven into the fabric of reality itself. The universe at its deepest level is intrinsically fuzzy. Certainty, the kind of absolute knowledge we crave, is not just difficult to achieve, it's impossible. At first, this might sound like a frustrating limitation, as though nature is deliberately hiding information from us playing a cosmic game of keep away. But the truth is more profound. The uncertainty principle isn't about what we can know, it's about what exists. Reality itself is blurred. A particle doesn't have a precise position and momentum simultaneously, because those properties at the quantum level are not both defined at the same time. Think of it this way. Imagine trying to take a perfectly sharp photograph of a child running across a field. If you use a fast shutter speed to freeze the motion, capturing exactly where the child is, at that instant, the image will be crisp and clear. But in doing so, you lose information about the motion. The photo shows position, but it tells you nothing about how fast the child was moving or in which direction. On the other hand, if you use a slower shutter speed to capture the motion, the child becomes a blur, a streak of movement across the frame. You can see the direction and speed, but now the exact position is lost, smeared across the image. The quantum world is like that photograph, except the blurriness isn't in the camera, it's in the child. The electron doesn't have a sharp position and a definite speed. It exists in a state where both are to some degree undefined, spread out across a range of possibilities. This has staggering consequences. For one, it means that nothing in the universe can ever be perfectly still. If a particle were completely motionless, its momentum would be exactly zero, a perfectly defined value. But if momentum is perfectly known, then position becomes completely uncertain, spread out infinitely across all of space. That's nonsensical. So the particle must always have some motion, some jitter, some residual energy that keeps it from settling into absolute stillness. This is why zero-point energy exists. Even at absolute zero, when all thermal energy has been drained away, particles still tremble with a faint, irreducible motion. The uncertainty principle forbids them from stopping completely. It's as if the universe itself has a case of restless leg syndrome, unable to sit perfectly still, no matter how hard it tries. And here's where it gets even stranger. If electrons could be perfectly motionless, atoms would collapse. Think about it. An electron orbiting a nucleus is in classical terms constantly accelerating, changing direction as it moves in a circle. Accelerating charges radiate energy. They should lose speed spiral inward and crash into the nucleus in a fraction of a second. Every atom in the universe should be unstable, collapsing in on itself almost instantly. But they don't. And the reason they don't is because electrons can never be pinned down to a precise position and zero momentum. They exist in a cloud of probability, spread out around the nucleus, always in motion, always uncertain. That uncertainty is what keeps them from falling in. The electron's intrinsic fuzziness, its refusal to be both here and still, is the scaffolding that holds matter together. In other words, uncertainty isn't a bug in the design of the universe. It's a feature. It's the very thing that allows atoms to exist, stars to shine, and you to be here reading these words. You could say the universe is like a hyperactive child, unable to sit still, always fidgeting, always in motion. It's not a flaw, it's vitality. If the cosmos could hold perfectly still, if every particle could settle into absolute certainty, reality would freeze into a lifeless, inert state. There would be no change, no transformation, no possibility of anything new. The restlessness, the jitter, the constant trembling at the quantum scale, that's what keeps existence alive. There's a deeper philosophical truth here, one that ripples far beyond physics. The idea that perfection is impossible, that certainty is a mirage, might sound bleak at first, but it's actually liberating. It means the universe is not a finished thing, not a static sculpture carved in stone. It's a living process, always becoming, always shifting, always open to possibility. The uncertainty principle tells us that nature doesn't deal in absolutes. It deals in probabilities, in ranges, in tendencies. And that openness, that refusal to be locked down, is what allows for complexity, for creativity, for the emergence of stars and galaxies, and eventually, improbably, life itself. Think of your own existence. You are not a fixed thing. You are a process, a pattern of atoms, constantly exchanging with the environment, electrons jittering in their clouds, quantum fields vibrating in intricate harmony. Every thought you have, every decision you make, arises from this restless foundation, from the tiny uncertainties that cascade upward through neurons and synapses into something as vast and mysterious as consciousness. You exist because the universe cannot be certain. You are in a very real sense made of uncertainty itself. And maybe that's the most beautiful thing about it. The same principle that forbids absolute knowledge also ensures that the future is not predetermined. The quantum fuzziness at the smallest scales means that reality, even at its most fundamental level, retains an element of spontaneity, of freedom. The dice are always rolling. The outcome is never fully written. This doesn't mean the universe is chaotic. Far from it. The uncertainty is governed by precise mathematical laws. It's not randomness in the sense of disorder, but randomness in the sense of openness, of potential waiting to unfold. And from that potential, from those countless tiny uncertainties compounding across time and space, emerges everything: the structure of atoms, the birth of stars, the evolution of galaxies, and the quiet miracle of a single thought forming in your mind. Perfection in the quantum world is not stillness, it's movement. It's not certainty, it's balance. The universe doesn't need to know everything to function beautifully. It only needs to keep dancing, to keep vibrating, to keep allowing the impossible and the improbable to flicker into being. So the next time you feel uncertain, adrift in a sea of unknowns, remember this: uncertainty is not a weakness. It's the very thing that makes you possible. The smallest uncertainties within you, the quantum jitters in your atoms, the restless fields that refuse to settle, they are what keep you alive, keep you changing, keep you becoming. It's the tiny uncertainties inside you, the quantum tremble in every atom, that make you more than a statue, more than a frozen moment. You are motion itself, possibility itself alive, because the universe refuses to stand still. By the end of the 19th century, physics felt nearly complete. The great minds of the era spoke of their field as though it were a grand cathedral, almost finished with only a few small decorative details left to add. Gravity had been explained by Newton. Electromagnetism had been unified by Maxwell. Thermodynamics had revealed the laws governing heat and energy. The universe, it seemed, ran on elegant, predictable mathematics. Everything could be measured, calculated, understood. There were a few loose threads, of course. Small puzzles that didn't quite fit. But most physicists assumed these were minor issues, irritating imperfections that would soon be smoothed away with better measurements or slightly refined equations. The building was nearly done. Soon they thought there would be nothing left to discover but more precise decimal places. One of those loose threads involved something deceptively simple: the light emitted by hot objects. When you heat a piece of metal, it glows. First a dull red, then orange, then yellow, and eventually, if you could heat it hot enough, a brilliant white. Scientists called these glowing objects black bodies, not because they were dark, but because they were perfect absorbers, soaking up all the light that fell on them before radiating it back out as heat and glow. The problem was that when physicists tried to calculate exactly how much light a black body should emit at different wavelengths, the equations broke down in spectacular fashion. According to classical theory, as the wavelength grew shorter, moving toward the ultraviolet end of the spectrum, the amount of energy radiated should increase without limit. The math predicted that every warm object, even something as mundane as a piece of coal, should pour out infinite energy in ultraviolet light. This was absurd. Clearly, it wasn't happening. You don't get incinerated by infinite radiation every time you stand near a warm stove. The prediction was so wildly wrong that physicists gave it a darkly humorous name: the ultraviolet catastrophe. Enter Max Planck. He was a careful, conservative German physicist, the kind of man who valued order, precision, and respect for tradition. He was not a revolutionary by temperament. He didn't wake up wanting to overturn centuries of established physics. He simply wanted to fix a problem, to find the small correction that would make the equations behave. In the year 1900, Planck was deep in this puzzle, tweaking formulas, adjusting constants, searching for the missing piece. And then, out of what he later called an act of desperation, he tried something radical. He proposed that energy could not be emitted or absorbed in a continuous stream, like water flowing from a tap, but only in discrete chunks, tiny packets that could not be divided further. He called each packet a quantum, from the Latin word for how much. The size of each quantum, he said, depended on the frequency of the light. High frequency meant large packets. Low frequency meant small ones. And crucially, nothing in between was allowed. Energy came in steps like a staircase, not a ramp. When Planck plugged this idea into his equations, something extraordinary happened. The math worked perfectly. The predicted spectrum matched experimental results with stunning precision. The ultraviolet catastrophe vanished. The infinite energies disappeared, replaced by a smooth, finite curve that described exactly what was observed in laboratories. He had solved the problem, but in doing so, he had introduced something deeply unsettling. Planck himself hated the idea. He didn't believe it, not really. He saw it as a mathematical trick, a provisional fix that would eventually be replaced by something more sensible, something that didn't violate the smooth, continuous nature of energy that classical physics had always assumed. In letters and lectures, he downplayed the significance of his discovery, treating it almost apologetically, as though embarrassed by what he'd been forced to propose. He wanted to save classical physics, not destroy it. He imagined himself as a repairman, patching a crack in the cathedral wall, not as someone placing dynamite at its foundation. But the crack he'd found ran deeper than anyone realized, and the patch he applied, reluctant and desperate as it was, would eventually bring the whole structure down, making way for something stranger and more beautiful than anyone in 1900 could have imagined. What Planck didn't fully grasp at the time was that he had touched something fundamental. Energy, the most basic currency of the universe, was not infinitely divisible. It had a granular structure, a texture at the smallest scales. Reality beneath its smooth appearance was pixelated digital, built from tiny, indivisible units. This was not a minor adjustment. It was a hint that the universe operated on principles radically different from anything classical physics had imagined. But Planck, cautious and conservative, couldn't see it yet. He spent years trying to reconcile his quantum hypothesis with classical theory, searching for a way to make it less radical, less strange. He never quite succeeded. It would take others, younger and bolder, to seize upon his reluctant discovery and carry it forward into territory Planck never wanted to explore. The quantum revolution he sparked would eventually consume the old physics, entirely reshaping humanity's understanding of energy matter and reality itself. But in 1900, all of that lay in the future. Planck had simply done what any good scientist does when the data refuses to cooperate. He followed where the math led, even though he didn't like the destination. There's something almost tragic about it. A man who loved order, who revered the classical traditions of physics, forced by sheer intellectual honesty to propose an idea that would dismantle everything he held dear. He wanted certainty, continuity, the comfort of smooth equations, and predictable outcomes. Instead, he opened a door to a world of probabilities, uncertainties, and quantum jumps. Sometimes the right answer is the one you don't want to hear, and sometimes, in reluctantly accepting that answer, you change the world. Planck's quantum, that tiny, indivisible packet of energy, was the first crack in the smooth facade of classical physics. And though he spent the rest of his life trying to repair it, the crack only widened until eventually the whole edifice of 19th century certainty came tumbling down, replaced by the strange, shimmering architecture of the quantum world. But Planck's quantum was still just a mathematical abstraction, a trick to make the numbers work. It would take someone else, someone working far from the ivory towers of academic physics, to prove that quanta were not just convenient fictions, but real tangible pieces of the universe. And that light itself, the most familiar thing in the world, was stranger than anyone had dared to imagine. In 1905, Albert Einstein was 26 years old, recently married and working long hours at the Swiss Patent Office in Bern. His job was to examine patent applications for new inventions, devices, machines, contraptions of all kinds, and determine whether they were original enough to be granted legal protection. It was steady work, respectable enough, but it wasn't glamorous. He spent his days reading technical descriptions of electromagnetic regulators, improved typewriters, and mechanisms for synchronizing clocks. But Einstein had a secret. While his official job was evaluating other people's inventions, his real work happened in the evenings late at night and during stolen moments at his desk when the patent applications grew dull. He was thinking about the universe, and in that single year 1905, he would publish 4 papers that would change physics forever. One of them explained Brownian motion, the jittery movement of pollen grains in water, proving once and for all that atoms were real. Another introduced the special theory of relativity, showing that space and time were not separate absolute things, but woven together into a flexible fabric that bent and stretched depending on how you moved through it. A third paper, a footnote to relativity, contained the most famous equation in history, E equals mc squared, revealing that matter and energy were interchangeable. But the paper that would eventually win him the Nobel Prize, not relativity, as most people assume, was about something simpler, stranger, and closer to everyday experience. It was about light. Scientists had been puzzled by a phenomenon called the photoelectric effect. When you shine ultraviolet light on certain metals, electrons are ejected from the surface, creating a tiny electric current. This wasn't surprising in itself. What was strange were the details. The intensity of the light, how bright it was, didn't determine how much energy the ejected electrons had. Only the color, the frequency mattered. A dim blue light could knock out energetic electrons, while a blazingly bright red light, no matter how intense, did nothing at all. Classical physics couldn't explain it. If light were a continuous wave, as everyone believed, then brighter light should carry more energy and should therefore eject more energetic electrons. But the experiments showed otherwise. It was as if the light carried its energy in discrete chunks, and only chunks above a certain size could do the job. Einstein, reading Planck's work, carefully realized what was happening. He took Planck's quantum idea, which Planck himself had proposed, reluctantly, and tried to minimize and pushed it further. What if Einstein asked the quantum nature of energy wasn't just a property of how matter emitted and absorbed light, but a property of light itself? What if light, that most wave-like of phenomena, was also made of particles? He called them light quanta. Today we call them photons. Each photon, Einstein proposed, carried a specific packet of energy determined by its frequency. Blue light, with its higher frequency, had energetic photons. Red light had less energetic ones. When a photon struck a metal surface, it could transfer its energy to an electron in a single all-or-nothing collision. If the photon's energy was high enough, the electron was freed. If not, nothing happened, no matter how many low-energy photons you threw at the surface. It was an audacious claim. For over a century, experiments had confirmed that light behaved like a wave. It could diffract, interfere, bend around corners. But Einstein was saying that light was also a particle, a tiny bullet of energy. Both things, somehow at once. The idea was met with skepticism, even ridicule. Even Planck, whose work had inspired Einstein, hesitated to accept it. But over the following decades, experiment after experiment confirmed Einstein's prediction. The photoelectric effect became one of the most precisely verified phenomena in modern physics. Light really was made of quanta. And here's the remarkable part. Einstein wasn't working in a prestigious university with access to expensive laboratories. He was a patent clerk scribbling equations on scratch paper during his lunch breaks, thinking about physics in the margins of his bureaucratic duties. He had no funding, no research assistance, no academic position, just curiosity, stubbornness, and an extraordinary ability to see through the surface of things to the hidden structure beneath. In fact, during that same miraculous year, he was juggling all three of those groundbreaking papers, at once moving between them as his mind wandered from one problem to another. In the mornings, he might be evaluating a patent for an electrical device. In the afternoons, he'd be thinking about the nature of time. In the evenings, he'd be working out the implications of light quanta. It's almost absurd, the sheer intellectual productivity of it. You could say his main job was reviewing machines, his side hustle, overturning the foundations of reality. The photoelectric effect wasn't just a theoretical curiosity. It became the basis for technologies that shape modern life. Every solar panel on every rooftop works because of the principle Einstein described. Photons strike a semiconductor, knock electrons loose, and generate an electric current. The automatic doors that open when you approach them use photoelectric sensors. The camera in your phone captures images by counting photons striking millions of tiny sensors. Even the pixels on the screen you're reading right now rely on the quantum interaction between light and matter. Einstein's insight, born in the quiet hours of a patent office in a small Swiss city, is embedded in the devices you use every day. The light quanta, he imagined those invisible packets of energy are being absorbed and emitted all around you every second, making the modern world possible. And yet, for all his brilliance, Einstein would spend the rest of his life uncomfortable with where his ideas led. He had helped birth quantum mechanics, but as the theory grew stranger, introducing probabilities, uncertainties, and particles that seemed to be in two places at once, he recoiled. He famously said, "God does not play dice with the universe," a protest against the randomness that quantum theory seemed to require. But the universe, it turned out, didn't need Einstein's approval. The quantum world he helped reveal kept unfolding, stranger, and more beautiful than even he could accept. There's a kind of poetry in that. The man who proved that light was both wave and particle, who showed that energy came in indivisible chunks, who rewrote the rules of space and time, spent his later years trying to prove that the quantum revolution he'd sparked had gone too far. He wanted a deeper theory, something deterministic and complete, something that would restore the certainty he felt slipping away. He never found it, and maybe that's fitting. The quantum world doesn't offer neat closure. It offers endless mystery, layer upon layer, each revelation opening new questions. So, the next time you glance at your phone, let a message load, or watch a video, remember this: the device in your hand works because of ideas that came from a patent clerk in 1905, a young man with wild hair and wilder thoughts who looked at light and saw not just waves, but particles, not just continuity, but quanta, and in doing so, gave us a glimpse of the universe's hidden clockwork. The phone in your hand, the screen lighting your face, the touch sensors responding to your fingertips, all of it works because of ideas born in the mind of a patent office clerk who spent his evenings rewriting physics. Einstein had shown that light was made of particles, but the atom itself still held secrets. How did electrons orbit the nucleus without collapsing? Why did different elements glow in such specific colors? To answer those questions, physics needed another leap, another mind willing to imagine the impossible. And this time, it would come from an unexpected place. A French prince who abandoned aristocracy for equations. Louis de Broglie was not supposed to become a physicist. Born into French aristocracy, the seventh duke of his family line, he was expected to follow tradition, perhaps diplomacy, perhaps the military, certainly something befitting a man of his station. Physics was for specialists, for academics toiling away in universities, not for princes. But de Broglie had always been drawn to ideas, to the abstract elegance of mathematics and the mysteries of the natural world. And in the early 1920s, still in his 20s, he began to wonder about something that had puzzled him since reading about Einstein's photons. If light, which everyone had always thought of as a wave, could also behave like a particle, then why couldn't the reverse be true? Why couldn't particles, things like electrons, also behave like waves? It was a wild thought. Particles were particles. They had mass. They occupied space. They moved along definite paths. Waves, on the other hand, were spread out, oscillating, capable of interference and diffraction. The two seemed as different as solid and liquid, as incompatible as fire and ice. But de Broglie was undeterred. In 1924, he submitted his doctoral thesis, proposing exactly that matter at the quantum level had a wave-like nature. Every particle, he argued, was associated with a wave, and the wavelength of that wave was inversely proportional to the particle's momentum. Fast-moving particles had short wavelengths, slow ones had long wavelengths, but they all had waves. His thesis committee didn't know what to make of it. The idea was so strange, so speculative, that they hesitated to approve it. In the end, they sent it to Einstein, who was by then the most famous physicist in the world, asking for his opinion. Einstein read it and was delighted. He immediately recognized the brilliance of the idea. It wasn't just clever, it was inevitable. If light could be both wave and particle, then symmetry demanded that matter should be able to do the same. De Broglie's proposal, Einstein wrote, was not just plausible, but probably correct. With Einstein's endorsement, de Broglie received his doctorate. But the physics community remained skeptical. Matter waves. It sounded more like philosophy than science. Where was the evidence? The evidence came soon enough. Experimenters fired electrons at crystals and watched them diffract, bending and spreading, just like light waves passing through a slit. The electrons weren't behaving like little billiard balls. They were behaving like ripples in water, interfering with themselves, creating patterns that only waves could make. De Broglie had been right. Particles were waves. Or rather, they were both depending on how you looked at them. The wave-particle duality that had once seemed like a paradox unique to light was in fact a universal truth. Everything in the universe, from photons to electrons, to, in principle, even you had both particle-like and wave-like properties. But what did these waves mean? What were they waves of? Enter Erwin Schrödinger, an Austrian physicist with a deep love of mathematics and a certain romantic streak. In 1926, inspired by de Broglie's work, Schrödinger set out to write an equation that could describe these matter waves mathematically. He wanted to know how they evolved, how they moved, how they interacted with forces like the electromagnetic pull of an atomic nucleus. The result was the Schrödinger equation, one of the most important equations in all of physics. It described the wave function, a mathematical object that captured the wave-like behavior of particles. The wave function wasn't a wave of water or air or any physical medium. It was a wave of probability. Its peaks represented places where a particle was likely to be found. Its troughs represented places where it was unlikely. The act of measuring, of observing the particle, caused the wave function to collapse, selecting one outcome from the many possibilities it described. This was a profound shift in thinking. In classical physics, particles had definite positions and velocities. You could, in principle, know exactly where something was and where it was going. But in quantum mechanics, particles existed in a haze of probability spread out across space, only crystallizing into a specific location when observed. Schrödinger's equation worked beautifully for the hydrogen atom. It predicted the exact energy levels that Bohr had proposed. But now they weren't just arbitrary rules. They emerged naturally from the mathematics. The electron wasn't orbiting like a tiny planet. It was a standing wave, a vibration wrapped around the nucleus, and only certain vibrations fit. Only certain harmonics were allowed. When physicists began to visualize these wave functions, they discovered something astonishing. The shapes were exquisite. The simplest orbital, the ground state of hydrogen, was a smooth sphere, a cloud of probability centered on the nucleus. But higher energy orbitals were stranger, more complex. Some looked like dumbbells, others like clovers, still others like intricate layered rings, surfaces of nodes and antinodes, peaks and valleys of probability. These shapes weren't arbitrary. They were solutions to Schrödinger's equation, the natural geometries that arose when waves were confined to the space around an atom. And they were beautiful, hauntingly, so like abstract sculptures carved from pure mathematics. If you've ever seen visualizations of atomic orbitals, the ones that show electrons as glowing clouds of color, you've glimpsed this hidden architecture. They look like modern art, like something Kandinsky might have painted, all flowing curves and symmetrical lobes. But they're not art, they're reality, or at least they're as close as we can get to visualizing the invisible quantum world. I know the story is starting to sound like fiction. A prince who becomes a physicist, a professor who writes an equation that turns particles into waves of probability, shapes so beautiful they could hang in a gallery. But here's the thing, it's all true, every word. Science at its most profound is stranger and more wonderful than any novel. What Schrödinger had shown was that the atom wasn't a machine, not a clockwork system of orbiting parts. It was a symphony, a resonance, a standing wave vibrating in three-dimensional space. And those vibrations defined not just where the electron was, but what it could become. This changed everything. Chemistry, once a catalog of reactions and properties, became a study of how these wave functions overlapped and interacted. Biology, the science of life, was revealed to be, at its deepest level, a dance of quantum probabilities. The proteins in your cells, the DNA that codes for your existence, the enzymes that catalyze every reaction, keeping you alive, all of it depends on the shapes and behaviors of electron clouds, on the solutions to Schrödinger's equation. The atoms in your brain, the ones firing in intricate patterns as you read these words, don't exist in one place. They exist everywhere. Their wave functions allow smeared across a cloud of probability. The electrons in your neurons aren't here or there. They're both simultaneously until the act of interaction collapses them into a definite state. In other words, the atoms in your brain aren't somewhere. They're everywhere at once, vibrating, resonating, holding the pattern that makes thought possible. It's a dizzying idea, but it's also quietly beautiful. You are not made of static things. You're made of waves, harmonies, probabilities, dancing in a delicate balance. And those waves, those mathematical sculptures, invisible to the eye, are what hold you together, what make you capable of awareness, of wonder, of reading these words, and contemplating your own existence. But even as Schrödinger's equation revealed the wave-like nature of matter, it left a troubling question unanswered. If particles are waves of probability, if reality is fundamentally uncertain, then what does that mean for the universe as a whole? Is everything just chance? And if so, what happens to cause and effect to the orderly chain of events we rely on? That question would spark one of the greatest intellectual battles of the 20th century, pitting two titans of physics against each other in a debate that would reshape our understanding of reality itself. Albert Einstein had helped create quantum mechanics. His work on the photoelectric effect had proven that light came in quanta. His endorsement of de Broglie's matter waves had paved the way for Schrödinger's equation. He was, in many ways, one of the fathers of the quantum revolution. And yet, as the theory matured, as it grew stranger and more complete, Einstein began to pull away. He didn't like where it was going. He didn't like the randomness, the probabilities, the idea that nature at its most fundamental level was governed not by deterministic laws, but by chance. In 1926, in a letter to his friend, Max Born Einstein wrote one of the most famous lines in the history of science: "God does not play dice with the universe." It wasn't just a casual remark. It was a statement of deep philosophical conviction. Einstein believed that reality had to be deterministic, that beneath the apparent randomness of quantum mechanics, there must be hidden variables, deeper laws that determined every outcome with perfect precision. The probabilities in quantum mechanics, he thought, were just a reflection of our ignorance, not a fundamental feature of nature. Niels Bohr, the Danish physicist who had proposed the quantized model of the atom, disagreed. Bohr had come to accept, even embrace, the strange implications of quantum theory. He argued that the probabilities were not a limitation of our knowledge, but an essential part of how the world worked. Particles didn't have definite properties until they were measured. The act of observation didn't just reveal reality, it helped create it. The two men, Einstein and Bohr, spent years debating this point, sometimes in person, sometimes in letters, always with respect and affection, but also with a profound and irreconcilable difference in how they saw the universe. Their debates became legendary. Einstein would propose thought experiments, clever scenarios, designed to expose contradictions or absurdities in quantum mechanics. Bohr would patiently dismantle them, showing that the theory, strange as it was, remained self-consistent. It was a kind of intellectual chess match, played out over decades with the nature of reality as the stakes. One of Einstein's most famous challenges came in 1935 in a paper co-written with Boris Podolsky and Nathan Rosen. It's now known as the EPR paradox, named after the initials of its authors. The paper described a scenario involving two particles that had interacted and then separated, moving far apart from each other. According to quantum mechanics, the particles remained entangled. Their properties correlated in such a way that measuring one instantly affected the other, no matter how far apart they were. Einstein called this spooky action at a distance. It seemed absurd. How could measuring a particle here instantaneously influence a particle on the other side of the galaxy? Surely, Einstein argued, this meant that quantum mechanics was incomplete. There must be hidden variables, properties that the particles possessed all along that determined the outcomes in advance. Bohr's response was characteristically subtle. He argued that the entangled particles weren't really separate. They were part of a single quantum system, described by a single wave function, and it was meaningless to talk about their individual properties until a measurement was made. The spookiness was only spooky if you insisted on thinking of particles as separate independent objects. But quantum mechanics didn't allow that. It demanded a more holistic view, one where the whole was more fundamental than the parts. The debate was more than just a disagreement about equations. It was a clash of worldviews. Einstein wanted a universe that was knowable, predictable, governed by clear causal chains. He wanted a reality that existed independently of observation, a cosmos that would be there even if no one was looking. Bohr, on the other hand, had come to accept that reality was participatory, that the observer and the observed were entangled, that questions about what really exists when no one is measuring were in a sense meaningless. What makes this debate even more poignant is that the two men were friends. They respected each other deeply. Einstein admired Bohr's brilliance and integrity. Bohr revered Einstein as one of the greatest minds in history. But they could not agree on this fundamental question, and neither could convince the other. For decades, their debate remained philosophical. There seemed to be no way to experimentally test whether Einstein's hidden variables existed or whether Bohr's more radical interpretation was correct. Quantum mechanics worked perfectly in practice. It predicted the behavior of atoms' molecules and light with stunning accuracy. But the deeper question, the question of what it meant, remained unresolved. Then in 1964, more than a decade after both Einstein and Bohr had died, a physicist named John Bell proved something remarkable. He showed that if hidden variables existed, if Einstein was right, then certain statistical correlations between entangled particles would be limited in a specific way. But if Bohr was right, if quantum mechanics was complete, and there were no hidden variables, then those correlations could violate Bell's limit. In other words, the question could be tested, and over the following decades, experimenters did exactly that. They created entangled particles, separated them, measured them, and checked the correlations. Again and again, the results violated Bell's inequality. The particles were more correlated than Einstein's hidden variables could explain. Quantum entanglement was real. The spooky action was not an illusion or a sign of incompleteness. It was a genuine feature of the universe. Einstein, for all his genius, had been wrong. Bohr, as strange as his view seemed, had been right. The universe does play dice, and sometimes those dice are entangled, their outcomes mysteriously linked across vast distances in ways that defy our classical intuitions. There's something humbling about this. Einstein, perhaps the greatest physicist who ever lived, spent the last decades of his life convinced that quantum mechanics was flawed, that a deeper, more complete theory would eventually be found. He never wavered in that conviction, and he was mistaken. It's a reminder that even the people we admire most, the ones whose insights have reshaped the world, can be wrong. Brilliance doesn't guarantee correctness, and sometimes the truth is stranger than even the most brilliant minds are willing to accept. But there's also something beautiful in the story. Einstein and Bohr, despite their profound disagreement, never stopped respecting each other. They argued fiercely, but with kindness, with curiosity, with a shared commitment to understanding the world. Their debate wasn't about ego. It was about truth, about pushing each other to think more clearly, to question more deeply, and in the end, their debate advanced physics. Even though Einstein was wrong about hidden variables, his challenges forced Bohr and others to sharpen their arguments to clarify what quantum mechanics really meant. The EPR paradox, intended to expose a flaw, ended up revealing one of the most profound and strange features of reality entanglement. So, maybe the lesson isn't just that Einstein was wrong. Maybe it's that being wrong, when done with rigor and honesty, can still move science forward. The questions we ask, even the ones that lead us astray, can illuminate truths we never expected to find. Sometimes the people you respect most, the ones who taught you to see the world differently, turn out to be wrong about the very things they cared about most. And that's not a failure. It's part of the process, the endless conversation that is science, where even being wrong in the right way can light the path forward. Einstein and Bohr had argued about the meaning of quantum mechanics, but the theory itself kept working, kept predicting, kept revealing new layers of reality. And as the 20th century unfolded, those predictions didn't just stay in textbooks. They became technologies, tools, devices that would reshape human civilization, proving that quantum mechanics, strange as it was, wasn't just philosophy, it was power. For decades, quantum mechanics lived primarily in the realm of thought. It was a theory, brilliant and strange, that explained atoms and light with breathtaking precision. But to most people, it seemed abstract, disconnected from daily life, a curiosity for physicists to debate in journals and lecture halls. Then, quietly, it began to escape the laboratory. The first revolution came with the transistor. In 1947, physicists at Bell Labs were trying to improve telephone switches, looking for a better way to amplify electrical signals. What they created almost by accident was a device that could control the flow of electrons using quantum mechanical principles. The transistor relied on semiconductors materials whose electrical properties emerge from the quantum behavior of electrons moving through crystal lattices, hopping between energy bands, tunneling through barriers. It was small, reliable, and used almost no power, and it changed everything. Transistors replaced vacuum tubes, those bulky glass components that had powered radios and early computers. They made electronics portable, affordable, ubiquitous. A single computer in the 1940s filled an entire room and required constant maintenance. Today, your phone contains billions of transistors, each one a tiny quantum switch, flipping on and off billions of times per second, processing information at speeds that would have seemed like magic just decades ago. Every email you send, every photo you take, every moment you spend scrolling through information, all of it is made possible by quantum mechanics, governing the movement of electrons through silicon. The digital age, the information revolution, the entire architecture of modern life rests on a foundation of quantum physics. Then came the laser. In 1960, Theodore Maiman built the first working laser, a device that produced a beam of light unlike anything seen before. Ordinary light from a bulb or the sun is chaotic, a jumble of wavelengths radiating in all directions. But laser light is coherent. The photons march in lockstep, all the same frequency, all in phase, moving together like a disciplined army. This coherence arises from quantum mechanics. Inside, a laser atoms are excited to higher energy levels, and when they release that energy as photons, they do so in a coordinated way, stimulated by other photons to emit light that's perfectly synchronized. It's quantum mechanics orchestrating light into harmony. Lasers now scan barcodes at checkout counters, cut steel in factories, perform delicate eye surgeries, transmit information through fiber optic cables at the speed of light, the beam of a laser pointer, the disk reader in your computer, the tools that reshape corneas and remove tumors. All are descendants of that first quantum insight that light could be tamed, aligned, made to sing in a single pure note. And then there's MRI, magnetic resonance imaging, one of the most powerful tools in modern medicine. When you lie inside an MRI machine, you're experiencing quantum physics firsthand. The machine generates a powerful magnetic field that aligns the spin of hydrogen nuclei in your body, primarily in water molecules. Then it sends pulses of radio waves, flipping those spins, and listens as they relax back into alignment, emitting faint signals. Different tissues relax at different rates, creating contrast, allowing doctors to see inside you without cutting, without radiation, just by listening to the quantum hum of hydrogen atoms. It's astonishing, really. The same quantum principles that Schrödinger used to describe electron clouds, that Bohr used to explain atomic spectra, are now being used to map the soft tissues of your brain, to detect tumors, to diagnose diseases, to save lives. But the quantum revolution isn't finished. In fact, it may be just beginning. Right now, in laboratories around the world, physicists and engineers are building quantum computers, machines that don't just use quantum mechanics incidentally, like transistors or lasers, but harness its deepest, strangest properties directly. And if they succeed, these machines could transform computation as radically as the transistor did 70 years ago. Here's the idea. A classical computer, the kind you're using right now, stores information in bits, each one either a 0 or a 1 on or off. Everything it does, every calculation, every image rendered, is built from sequences of these binary choices. A quantum computer uses qubits, quantum bits, and a qubit can be both 0 and 1 at the same time, held in a superposition of states. It's not that the qubit is secretly one or the other, and we just don't know which. It's genuinely both a cloud of possibility until it's measured. This means that a quantum computer, with just a few dozen qubits, can explore a vast number of possibilities simultaneously, like having many parallel versions of the computer working on the problem at once, each one following a different path, all paths existing at the same time. When the computation is finished, the system collapses into the answer, selecting the correct path from the multitude. It's a bit like asking a question and having 1,000 versions of yourself appear, each one exploring a different approach, then merging back together to give you the best answer. For certain kinds of problems involving searching large databases, factoring huge numbers, simulating quantum systems, this parallelism offers exponential speedups. Quantum computers could break current encryption schemes, rendering much of digital security obsolete. But they could also create new, unbreakable codes using quantum entanglement. They could simulate molecules with perfect accuracy, designing new drugs, new materials, new catalysts for clean energy. They could optimize complex systems, from traffic networks to supply chains to the training of artificial intelligence. But there's a catch, and it's a big one. Qubits are extraordinarily fragile. Remember decoherence, the way quantum states collapse when they interact with their environment. In a quantum computer, you need to keep qubits isolated perfectly still, coherent, for long enough to perform calculations. Even the tiniest vibration, the faintest heat, a stray photon can cause the delicate superposition to collapse, ruining the computation. Engineers cool quantum computers to temperatures colder than outer space, shield them from magnetic fields, isolate them in vacuum chambers, and still maintaining coherence for more than a few milliseconds is a monumental challenge. It's like trying to balance a pencil on its tip in the middle of an earthquake. Progress is being made slowly, carefully. Small quantum computers already exist. They can't yet outperform classical computers on practical tasks, but the gap is closing. The race is on to build machines with enough qubits, stable enough, coherent enough to cross the threshold into true quantum advantage. And when that happens, the world will change again. Every message you send, every search you perform, every secure transaction you make relies on quantum mechanics. The electrons in the chips, the photons in the fiber optic cables, the encryption algorithms protecting your data, all of it is quantum physics working quietly, invisibly holding the modern world together. You're already living in a quantum age. You just didn't realize it. So quantum mechanics has already transformed technology, shaping the devices we use, the medicine that heals us, the information networks that connect us. But there's something even more profound waiting to be explored, something that takes us beyond gadgets and into the very nature of existence itself. The way quantum energy doesn't just power machines, but composes reality, creating the structures, the patterns, the cosmic architecture of everything we see, from the smallest atom to the vastest galaxy. There's a reason we use musical metaphors when talking about quantum mechanics. It's not just poetic license. The parallels run deeper than language, touching something fundamental about how reality is structured. When Niels Bohr proposed his model of the atom, with electrons occupying specific energy levels around the nucleus, he was describing something remarkably similar to a vibrating string on a musical instrument. A guitar string, when plucked, doesn't vibrate at just any frequency. It produces specific notes, harmonics overtones that depend on the length and tension of the string. Only certain patterns fit. Only certain wavelengths resonate. Electrons in an atom behave the same way. They can't exist at arbitrary energy levels. They must occupy states where their wave-like nature forms a standing pattern, a resonance that fits perfectly around the nucleus. When an electron jumps from one level to another, it emits or absorbs a photon, a packet of light whose energy corresponds exactly to the difference between those two states. Each jump produces a specific frequency of light, and each element, with its unique arrangement of electrons and energy levels, produces a unique set of frequencies. Hydrogen emits one pattern, helium another, carbon, oxygen, iron, each has its own signature, its own spectral fingerprint. In a very real sense, each element has its own voice, its own timbre, its own acoustic identity. When you pass the light from a glowing gas through a prism, the rainbow you see isn't continuous. It's broken into discrete lines, bright streaks of color, separated by darkness. These are the notes. The atom can sing the only frequencies it's allowed to produce. Astronomers use these spectral lines to identify what distant stars are made of. They look at the light from galaxies millions of light years away and see the unmistakable signatures of hydrogen, helium, carbon elements that exist across the cosmos, all playing the same quantum melodies they play here on Earth. But here's where it gets even more interesting. In recent years, scientists have begun experimenting with something called sonification, the process of converting data into sound. They take measurements from quantum systems, atomic spectra, the vibrations of molecules, and translate them into audible frequencies that human ears can hear. The result is astonishing. Atoms, when their quantum states are converted into sound, produce tones, harmonies, rhythms that are genuinely musical. Some research teams have created compositions entirely from atomic data, letting the quantum world compose its own symphonies. The music is strange, alien, but undeniably structured, patterned, beautiful, in a way that feels both mathematical and organic. This isn't just an artistic exercise. There's a reason quantum systems sound musical when translated into audio. It's because they are, in a deep sense, vibrational. Everything at the quantum level is oscillation frequency resonance. The mathematics that describes a vibrating drum or a plucked string is remarkably similar to the mathematics that describes an electron in an atom. Now there's been a lot of talk in recent years about sound healing frequency therapy, the idea that certain vibrations can affect the body in therapeutic ways. Some of this strays into pseudoscience, making claims that aren't supported by evidence, but there's a kernel of truth beneath the hype. Sound is vibration. Your body is matter, and matter, at the quantum level, responds to vibrations in specific ways. Music therapy, when practiced carefully and scientifically, has shown real benefits for stress reduction, pain management, even neurological recovery, not because of mystical frequencies, but because sound affects the nervous system, which affects hormone release, which affects healing. It's a chain of physical causation, each link grounded in biology and physics. But let's be clear, atoms don't heal you because they're tuned to 432 hertz, or because they resonate with cosmic vibrations. That's wishful thinking, dressed up in scientific language. The real science is more subtle, more grounded, and ultimately more interesting than the mysticism. What is true, genuinely and scientifically true, is that your body is a kind of orchestra. You're made of roughly 37 trillion cells, each one a buzzing hive of molecular activity. Inside each cell, proteins fold and unfold enzymes, catalyze reactions, electrons hop between energy levels, all in intricate, coordinated rhythms. Your neurons fire in synchronized patterns. Your heart beats in regular tempo. Even your breathing follows a rhythm, a cadence that mirrors the rise and fall of tides, the oscillations of quantum fields. If you could somehow hear all of it at once, the quantum hum of your atoms, the electrical pulses of your nerves, the mechanical vibrations of your cells, it would sound like a vast polyphonic symphony, millions of voices blending into a single coherent whole. You are not a thing. You are a performance, a living, breathing arrangement of frequencies all playing together in delicate balance. And every element in your body, every atom of carbon, hydrogen, oxygen, nitrogen, carries its own quantum signature, its own note in the cosmic scale. The calcium in your bones rings at one frequency, the iron in your blood at another. Together, they form chords, harmonies, a composition that is uniquely, unmistakably you. The atoms in your body, all 37 trillion cells worth, aren't just sitting there. They're vibrating, humming, playing their parts in an orchestra so vast and intricate that even the greatest symphony ever written is just a pale echo of the music happening inside you right now. But if atoms are musical instruments, then life itself might be the composer using quantum mechanics, not just passively, but actively harnessing its strange properties to build the machinery of biology in ways scientists are only beginning to understand. For a long time, scientists assumed that quantum mechanics belonged to the cold, sterile world of physics labs, not the warm, messy realm of biology. Living systems seemed too hot, too wet, too chaotic to preserve the delicate quantum states that physicists worked so hard to isolate in their experiments. Quantum coherence required near absolute zero temperatures, perfect isolation, the kind of conditions you'd never find inside a cell. But life, it turns out, is more clever than we gave it credit for. The first hint came from photosynthesis, the process by which plants convert sunlight into chemical energy. It's one of the most important reactions on Earth, the foundation of nearly every food chain, the source of the oxygen you're breathing right now. And it's astonishingly efficient. When a photon strikes a chlorophyll molecule in a leaf, nearly 100% of its energy is captured and transferred to the reaction center, where it's stored as chemical bonds. For decades, scientists assumed this efficiency came from trial and error, from the photon's energy bouncing randomly between molecules until it happened to find the right destination. But in the early 2000s, researchers using ultra-fast lasers discovered something extraordinary. The energy wasn't moving randomly at all. It was exploring multiple pathways, simultaneously existing in a quantum superposition, testing all possible routes at once before collapsing into the most efficient one. This is quantum coherence, the same phenomenon that makes quantum computers potentially powerful. And it's happening inside every green leaf, every blade of grass, every photosynthetic bacterium at room temperature, in wet, noisy, biological environments that should, by all classical reasoning, destroy such delicate quantum states instantly. Plants, it seems, figured out quantum computing millions of years before humans did. Then there are birds. Migratory species, like the European robin, travel thousands of kilometers each year, navigating with extraordinary precision. For a long time, no one knew how they did it. The Earth's magnetic field is far too weak for birds to sense it through ordinary means. The answer appears to lie in their eyes. Inside the retina, there are molecules called cryptochromes that, when struck by blue light, form pairs of entangled electrons. These entangled particles are sensitive to magnetic fields in a way that depends on quantum mechanics. The orientation of the Earth's field affects how long the entanglement lasts, subtly changing the chemical signals sent to the bird's brain. In effect, the bird can see the magnetic field not as a color, but as a faint pattern overlaid on its visual field, a quantum compass built into its biology. It's navigating using entanglement, one of the strangest and most fragile phenomena in physics, while flying through storms and across continents. And then there are enzymes, the molecular machines that make biochemistry possible. Many enzymes work by moving particles, protons, electrons, from one molecule to another. Sometimes the barrier between molecules is too high for particles to cross classically, so they tunnel quantum mechanically, slipping through walls that should be impenetrable. This happens constantly in your body. The enzymes that help you digest food, the ones that repair your DNA, the ones that produce energy in your cells, many of them rely on quantum tunneling to function. Without it, the reactions would be too slow, too inefficient to sustain life. There's even emerging evidence that your sense of smell, might involve quantum effects. One theory suggests that when an odor molecule binds to a receptor in your nose, the receptor detects not just the molecule's shape, but also its vibrational frequency, using a kind of quantum resonance to distinguish between molecules that look identical but vibrate differently. The evidence is still debated, but if true, it would mean you're smelling quantum vibrations every time you catch the scent of coffee, or rain, or roses. And then there's DNA repair. Your genetic code is constantly being damaged by radiation chemical reactions, copying errors. Yet cells have elaborate mechanisms to find and fix these errors. Some research suggests that the proteins involved in scanning DNA for damage use quantum coherence to search multiple sites simultaneously, making the process far faster and more accurate than classical chemistry alone would allow. All of this raises a fascinating question. Could consciousness itself be quantum? In the 1990s, physicist Roger Penrose and anesthesiologist Stuart Hameroff proposed a controversial theory. They suggested that consciousness might arise from quantum processes happening inside microtubules, tiny structural components inside neurons. According to their theory, these microtubules could maintain quantum coherence, long enough to perform computations that classical neurons couldn't, giving rise to the subjective experience of awareness. It's a bold idea, and it's important to say clearly it's speculative. Most neuroscientists are skeptical. There's no strong experimental evidence for it yet, and the brain seems far too warm and noisy to sustain the kind of quantum coherence the theory requires. But here's the thing. We once said the same thing about photosynthesis and bird navigation and enzyme catalysis, and yet life found a way. So while we should be cautious, while we should demand evidence and avoid mystical thinking, we shouldn't dismiss the possibility entirely. What we do know, what's been proven beyond doubt, is that life doesn't just tolerate quantum mechanics. It exploits it. Evolution has found ways to harness uncertainty, superposition, tunneling, entanglement, using them to build systems more efficient, more precise, more elegant than anything classical physics alone could achieve. I know this section sounds like science fiction. Quantum coherence in plants, entanglement in bird eyes, tunneling in your cells, consciousness as a quantum phenomenon. It feels too strange to be true. But here's the remarkable part. Most of it has been experimentally verified. These aren't just theories, they're observations. Scientists have measured the quantum coherence in photosynthesis. They've detected the magnetic sensitivity in cryptochromes. They've watched enzymes tunnel through barriers. Life, it turns out, is quantum, not metaphorically, literally. Every breath you take involves thousands of quantum events. Electrons tunneling through membranes, molecules transitioning between energy states, photons absorbed and re-emitted, the oxygen entering your lungs, the glucose feeding your cells, the electrical signals racing through your nerves. All of it is choreographed at the quantum level, a dance of probabilities collapsing into the miracle of metabolism. Every breath you take is a quantum miracle, billions of particles, tunneling, transitioning, entangling, collapsing into the single, seamless rhythm that keeps you alive. And if life on Earth has learned to play with quantum mechanics, using its strange rules to thrive in a classical world, then perhaps the universe itself, on the grandest scales imaginable, is also shaped by quantum processes, not just in atoms or cells, but in the very fabric of space and time. The Big Bang was not an explosion in space. It was an explosion of space. This is one of the hardest ideas in cosmology to grasp, because our intuition wants to place the beginning somewhere, to imagine a point in a vast darkness where everything suddenly appeared. But there was no darkness. There was no somewhere. Space itself, the stage on which everything happens, came into being, along with time, matter, and energy. Before the Big Bang, there was no before. The question of what existed prior is like asking what's north of the North Pole. The coordinates don't extend that far. But here's where quantum mechanics enters the story. In the first fraction of a second after the universe began, something extraordinary happened. The cosmos underwent a period of exponential expansion called cosmic inflation. In less than a trillionth of a trillionth of a trillionth of a second, 10 to the power of negative 32 seconds, the universe grew from smaller than an atom to larger than a galaxy. Space itself stretched faster than light, not because anything was moving through space, but because space was expanding, carrying everything with it. And during that brief, violent expansion, something subtle and profound occurred. The quantum vacuum, that restless sea of fluctuations we explored earlier, was magnified. Tiny random jitters and energy fluctuations so small they should have stayed buried at the quantum scale were suddenly blown up to cosmic proportions. Imagine taking a microscopic wrinkle in a piece of fabric and stretching the fabric until that wrinkle becomes a mountain range. That's what inflation did to quantum fluctuations. It took the smallest possible variations in energy density and inflated them into regions of space that were slightly denser or slightly less dense than their surroundings. Those tiny differences, 1 part in $100,000, became the seeds of everything. The denser regions had slightly more gravity. They pulled in surrounding matter. Over millions of years, they collapsed into clouds of gas, which collapsed into stars, which gathered into galaxies. The less dense regions became voids, vast empty spaces between the galaxies. Every structure in the universe, every cluster of galaxies, every supercluster, every filament in the cosmic web traces back to those original quantum fluctuations. The architecture of the cosmos is quite literally frozen quantum noise. We have a photograph of this. Well, not exactly a photograph, but close enough. The cosmic microwave background, or CMB, is the faint afterglow of the Big Bang light that has been traveling through space for 13.8 billion years. When we map it with sensitive instruments, it appears nearly uniform in all directions, a soft glow of microwave radiation filling the sky. But when you look closely, there are tiny variations in temperature hotspots and cold spots, differences of millionths of a degree. These variations aren't random. They're the imprint of those primordial quantum fluctuations stretched and frozen into the fabric of space, a snapshot of the universe when it was just 380,000 years old. Scientists have analyzed this pattern in exquisite detail. They can measure the sizes and distributions of the hot and cold spots, and from that infer the conditions of the early universe, the rate of expansion, the density of matter and energy, the strength of the original quantum fluctuations. And what they've found is astonishing. The pattern matches almost perfectly the predictions of quantum mechanics applied to the inflationary universe. The fingerprints of quantum jitter are written across the sky. This raises a dizzying possibility. If quantum fluctuations can create galaxies, can they create universes? Some interpretations of quantum mechanics, particularly the many worlds, interpretation suggests that every quantum event, every moment, when a wave function could collapse in multiple ways, actually does collapse in all possible ways, each outcome branching into a separate reality. According to this view, the universe constantly splits, creating an unimaginable multitude of parallel worlds, each one as real as this one, each following a slightly different path. If that's true, then the quantum fluctuations that seeded our universe might have seeded countless others. Each fluctuation, each quantum jitter in the primordial vacuum could have inflated into its own cosmos a bubble of space and time disconnected from ours, with its own laws, its own constants, its own galaxies and stars. This is the multiverse hypothesis, and while it's speculative, while it stretches beyond what we can currently observe or test, it follows naturally from the mathematics of quantum mechanics and inflation. If those theories are correct, then the multiverse isn't just possible, It's almost inevitable. Think of it like soap bubbles forming in a foam. Each bubble is a universe, inflating from the quantum froth, expanding, evolving, perhaps eventually popping or collapsing, or simply drifting away into isolation. Our universe is one bubble among countless others, each one born from the same restless quantum energy, each one a variation on the theme of existence. It's a humbling image, and yet there's something comforting about it too. If the multiverse is real, then existence isn't a one-time accident. It's an ongoing process, a constant creation, the universe endlessly exploring possibilities, trying out every variation, every configuration, every path. And you reading these words right now exist because one of those quantum fluctuations 13.8 billion years ago happened to have the right properties to collapse into stars, planets, and eventually life. You are here because the universe at its birth couldn't sit still, because quantum mechanics demanded fluctuation, because randomness amplified by inflation became structure. You exist because the universe couldn't stand still 13.8 billion years ago, because it trembled at the quantum level. And those trembles magnified across time and space became galaxies, stars, planets, and eventually, improbably, you. But if quantum mechanics shaped the universe's past, what about its future? To understand where we're going, we need to confront one of the deepest mysteries in cosmology, a force so pervasive it makes up most of the universe, yet so poorly understood that scientists can barely agree on what to call it. The universe is not slowing down, it's speeding up. This discovery, made in the late 1990s by astronomers studying distant supernovae, was so unexpected that at first many scientists didn't believe it. For most of the 20th century, cosmologists had assumed that the expansion of the universe set in motion by the Big Bang would gradually slow over time as gravity pulled everything back together. The question wasn't whether the expansion would stop, but when. But the data told a different story. Distant galaxies weren't just moving away from us. They were accelerating, receding faster and faster, as though something was pushing them apart, counteracting, gravity driving space itself to expand at an ever-increasing rate. That something is called dark energy, and it's one of the most profound puzzles in modern science. Here's what we know. Dark energy makes up roughly 70% of the total energy content of the universe. Dark matter, the invisible gravitational scaffolding that holds galaxies together, accounts for another 25%. Everything else, all the stars, planets, gas, dust, light, everything we can see is less than 5% of the cosmos. In other words, the universe is dominated by things we don't understand. And the biggest mystery of all is dark energy. What is it? Honestly, we don't know. There are hypotheses, educated guesses, mathematical models, but no definitive answer. One possibility is that dark energy is the cosmological constant, the term Einstein added to his equations of general relativity to make the universe static. He later called it his greatest blunder, but it might turn out to be his most prescient insight. The cosmological constant represents the energy of empty space itself, a kind of baseline pressure built into the vacuum. If that's true, then dark energy is closely related to the zero-point energy we discussed earlier. It's the quantum hum of the vacuum, the restless fluctuation of fields that never quite settle to zero. And as space expands, the total amount of vacuum energy increases because there's more space, and each bit of space carries the same energy density. The problem is the numbers. When physicists try to calculate how much vacuum energy should exist based on quantum field theory, they get a number that's absurdly catastrophically large, roughly 10 to the power of 120 times bigger than what we observe. It's called the cosmological constant problem, and it's arguably the biggest mismatch between theory and observation in all of science. Why is the vacuum energy so much smaller than predicted? No one knows. Some suggest there's a mechanism as yet unknown that cancels out most of the quantum contributions, leaving only a tiny residue. Others think our understanding of quantum fields or gravity must be incomplete. Another possibility is that dark energy isn't constant at all. Maybe it's a dynamic field, something that changes over time, growing stronger or weaker as the universe evolves. Physicists call this hypothetical field quintessence, after the ancient Greek idea of a fifth element beyond earth, water, air, and fire. If dark energy is quintessence, then its behavior could change. It might weaken, allowing gravity to eventually slow the expansion. Or it might strengthen, tearing the universe apart faster and faster until even atoms are ripped to shreds in an event called the Big Rip. And then there's a third option. Maybe Einstein's theory of gravity itself needs modification. Perhaps on the largest scales across billions of light years, gravity doesn't quite work the way general relativity predicts. Maybe there's an additional term, a correction that causes the acceleration we observe without invoking any mysterious energy. So, what does the future hold? If dark energy remains constant, the universe will continue expanding forever, gradually cooling, thinning until stars burn out, galaxies fade, and space becomes an endless, cold void. This is called the Big Freeze, or heat death, the slow, gentle ending of everything. If dark energy grows stronger, the expansion will accelerate without limit, eventually overcoming not just gravity between galaxies, but gravity within them, within solar systems, within atoms. Space will stretch so violently that matter itself is torn apart. This is the Big Rip, a violent, catastrophic end. If dark energy weakens or reverses, gravity might eventually win, pulling everything back together into a big crunch, a mirror image of the Big Bang, where space collapses, matter compresses, and perhaps in some theories, a new universe is born from the ashes of the old. We don't know which future awaits. The universe is still revealing its secrets, and dark energy is the biggest secret of all. It's almost funny in a cosmic sort of way. The universe is like a shopper on Black Friday, endlessly expanding its cart, grabbing more space, more emptiness, filling itself with vacuum, as though there's a sale on nothingness. And we're along for the ride, watching galaxies slip beyond the horizon, one by one into the unreachable distance. Right now, at this very moment, the space between you and the most distant galaxies is growing, not because anything is moving, but because space itself is stretching, inflated by dark energy, pushing everything apart. The universe is expanding beneath your feet, though you'll never notice because locally, within our galaxy, within our solar system, gravity holds things together. But on the largest scales, across the voids, Between galaxy clusters, space is winning. And as time goes on, the night sky will grow emptier, lonelier, until distant observers, if they exist, might never know that other galaxies ever existed. The distance between you and the farthest galaxy is growing right now, stretching invisibly, silently, as dark energy pushes the fabric of space outward, carrying the horizon of the universe ever farther beyond reach. And yet, for all this mystery, for all the unknowns about dark energy and the universe's fate, there's one thing we do know with absolute certainty: energy in all its forms is conserved, never created, never destroyed, only transformed. And that truth brings us full circle back to the beginning, to the simple, elegant law that ties everything together. We've traveled a long way together, from the desperate hypothesis of Max Planck to the expanding edge of the cosmos. We've watched quantum energy emerge from mathematical abstraction into the foundation of reality itself. And now, as we near the end, it's time to gather the threads to see how everything connects, how the smallest and largest scales mirror each other in a quiet, beautiful symmetry. At the heart of it all is a single principle: the conservation of energy. It's one of the simplest, most profound laws in physics. Energy cannot be created. It cannot be destroyed. It can only change form, flowing from one state to another, transforming endlessly, but never disappearing. This law holds everywhere, from the nucleus of an atom to the birth of a galaxy. The photon that strikes your eye was not conjured from nothing. It came from somewhere. A light bulb, a star, the decay of an excited atom. And when it's absorbed, its energy doesn't vanish. It becomes heat motion, a cascade of chemical reactions in your retina that eventually becomes the experience of seeing. Matter, as Einstein showed, is just energy in a different disguise. The atoms in your body, the ones that were replaced and exchanged, as we discussed in the beginning, are temporary vessels for energy that has existed since the Big Bang. The carbon in your cells was forged in stars. The hydrogen in your water was born in the first minutes of the universe. You are made quite literally from recycled starlight, from energy that has flowed through a billion different forms before settling for a brief moment into the pattern called you. And when you die, that energy won't disappear. It will simply move on, becoming heat, becoming soil, becoming food for other organisms, cycling through the biosphere, eventually radiating back into space as infrared light joining the cosmic background, continuing the endless transformation. Nothing is ever truly lost. Energy only changes its costume, slipping from one role to another in the grand performance of existence. But conservation is just the foundation. What makes quantum energy so remarkable is not just that it's conserved, but how it behaves, the strange and beautiful ways it manifests at every scale. And now, quantum mechanics is pointing toward new frontiers, technologies that will reshape the future, just as transistors and lasers reshaped the past. Quantum internet is coming. Instead of sending information as classical bits, vulnerable to interception and error, we'll send it as entangled photons, particles whose states are fundamentally linked, immune to eavesdropping, because any attempt to intercept them destroys the entanglement, alerting both sender and receiver. Communication will become not just faster, but fundamentally more secure, protected by the laws of quantum mechanics themselves. Quantum sensing will allow us to detect the faintest signals imaginable. Gravitational waves, ripples in space-time caused by colliding black holes can already be measured, but quantum sensors exploiting superposition and entanglement will detect even subtler distortions, mapping the universe's gravitational landscape with unprecedented precision, perhaps even sensing the gravitational hum of the Big Bang itself. Quantum biology is still in its infancy, but the potential is staggering. If we can understand how plants harness quantum coherence for photosynthesis, we might design artificial systems that capture solar energy with perfect efficiency. If we can decode how birds navigate with entanglement, we might build sensors that detect magnetic fields with exquisite sensitivity. If enzymes use quantum tunneling to catalyze reactions, perhaps we can design new drugs, new materials, new chemical processes that work faster, cleaner, more efficiently than anything classical chemistry allows. The quantum revolution is not finished. It's barely begun. And beneath all of this, beneath the technology and the theory, there's a deeper truth of philosophical insight that quantum mechanics offers if you're willing to sit with it quietly. You are not separate from the universe. You are the universe observing itself. The atoms in your brain, the electrons firing in your neurons, the thoughts emerging from quantum fields, collapsing into classical states, all of it is the cosmos, thinking, feeling, wondering about its own nature. The energy that powers your heartbeat, that lights your mind, that holds your body together, came from the Big Bang. It flowed through stars, through space, through generations of life, arriving at last in the form of you. And when you're gone, it will flow onward, joining the great river of transformation that has no beginning and no end. You are a pattern in the flow, a temporary coherence in the endless exchange of energy and form. But the pattern matters. It matters that you exist, that you wonder, that you ask questions about light and atoms and the nature of time. Because in doing so, you are the universe awakening to itself, quantum energy folding back to contemplate its own existence. There's a kind of grace in that, a reassurance. Nothing, you are nothing you've experienced, will be lost. It will simply change, merge back into the great symphony, become part of something new. The energy that is you right now, reading these words, feeling this moment, will persist transformed, but undiminished, woven into the fabric of everything that follows. The universe is not a cold, mechanical system, winding down toward silence. It's a living process, endlessly creative, endlessly becoming. And you are not a spectator, watching it unfold. You are part of the unfolding of voice, in the chorus, a note, in the infinite song. So, as you close your eyes tonight, as you settle into rest, remember this. You are not silent. You are not still. At every level, from the quantum trembling of your atoms to the slow rhythm of your breath, you are motion. You are energy. You are transformation. The universe, vast and ancient, flows through you. And for a little while, in this brief, improbable moment, it has arranged itself into a pattern that can think, that can feel, that can look back at the stars and recognize its own light shining there. You are not separate from the cosmos. You are its voice, its eyes, its momentary awareness. And when you breathe, when you wonder, when you simply exist, you are the universe waking up to itself, quantum energy folding inward to behold its own beauty. And when you close your eyes tonight, remember this: you are never truly silent. At every level, from the quantum hum of your atoms to the slow rhythm of your heartbeat, you are a symphony, a living composition that the universe is playing and will continue to play in endless variation, long after this particular melody has faded into the next.